Alright, what is up y'all? My name is Jay, and today I have a quick little video for you on Laplace Transforms for solving differential equations. So let's get started. Imagine a box. This box is a translator, a mathematical translator. So what we can do is we can shove a function into it, any function. And, we do some curly L stuff, and out of it, we get the same function, but in a different mathematical language, so to speak. Consequently, we can also stick this function back into the translator. We do this L-1, and out we get the original function. The key here is that those two are the same function, just in different mathematical languages we call spaces. Our new function is what we call Laplace space, since we used a Laplace transform, which is that curly L, to get there. Now, how do we do the transformation? Well, it's pretty simple. We use this formula. Stick f of t in there, and out we get f of s. Great, but we don't like that. And we don't have to, because someone else already did the work for us. In these tables, on the left of each screenshot, you have your small f of t, and on the right, you have your big F of s. They're the same thing, they're just in these different mathematical languages we call spaces. The one on the right is in what we call Laplace space, and on the one on the left is what I'm just calling regular space, because that's what we're used to. Now, how can we use this to solve differential equations? It's right here. This is really cool, because on the left, you see we have expressions with y prime and y double prime, and on the right, we got rid of all the primes and double primes. Let me show you how we can use this to solve a differential equation with an example. We love examples. Here we have a problem. Second order differential equation, some initial conditions. Cool. Let's get started. So, Laplace transforms function much the same as a derivative from Calc 1. You can apply it to every term in an equation, manipulate it, solve for what you need. So, let's do that. We take a Laplace transform of every single term, translating it to what we're calling Laplace space. So let's pull out some constants and then use the tables to manipulate it a little bit. So let's plug in that expression for cosine of t and for y double prime. And that gives us this. And this is really cool because now we've gotten rid of all the derivatives. Now we can just solve for that Ly, translate it back into regular space, and boom, we have our solution. So let's do that. Let's plug in some initial conditions. That gives us this. Solve for Ly, factor it out there. Divide both sides by s squared plus 4, and that gives us this equation. Now, theoretically, we could take an inverse and get our y equals garbage. And y equals garbage is good because y equals garbage is our solution. But we need to manipulate it before we can do that. So, let's use our good friend, partial fractions. We love partial fractions, right? Multiply both sides by the denominator, set up a system of equations, get our constants, and out we get this. The key here is that this expression that's in the box is the same as what's on the left here, except this we can take an inverse of. So let's do that. When we take an inverse, L and L-1, it seems intuitive that they cancel each other out, right? And from the tables, we know that this is true. And consequently, we know that this is true. And this L-1 of s over s squared plus a squared looks very similar to what we have on the right side of our equation. So let's manipulate it to look like that. Pull out a negative of the first term. 4 is actually 2 squared, and that becomes negative cosine of 2t. Second term, we do something similar. It becomes the cosine of t. Now let's put it all together. Our first term is going to become y. Our second term is going to become negative cosine of 2t. And our third term is cosine of t. This is our solution. We just found it. Let's review what we did to get there. So, first thing we did was we were given a problem. First thing we did to the problem was we applied a Laplace transform and solved for that Ly. That got us this. Then we manipulated it to a form we can use tables to take an inverse. And that was this. Recall that was the partial fractions. Then we just took an inverse. And that got us our solution. This is the process that you should follow to solve differential equations using Laplace transforms. Take the Laplace of all terms, take an inverse, and boom, you got your solution. I do have some additional resources. On the top, I have the tables. The second link's got extra lessons, examples. Laplace transforms of delta functions, heaviside functions, higher order, stuff like that. Hope this helped. Thank you.